Okay, let's get started. So, how how was the midterm? Hopefully, you all did well.
It's fine. Matthew, could you like talk about homework today?
Homework. What section is it on?
I think it's like 37, like section 5, I guess.
Section 5. Let me see. So, okay, let me go to the book. What problem number? What's the
30 and 37.
30 and 37?
Because I don't remember like we talked about the center of the group.
37 doesn't have center, right? It's about the. Am I looking at the right problem? So let me go. Let me share screen. So right here, 37, I don't see the word center. It's just about the dihedral group, right?
Oh, I mean like center is like in the problem 33, but I think I figured it out. But yeah, but I was trying to ask 33.
Yeah. I think I was gonna go over center of dihedral group
Okay.
today,
Yeah, sure, sure,
but
sure. Maybe after
yeah.
that.
Okay. Yeah. Okay. So let's get started. So DN, and part of it is problem 37, so I could probably go over that. Symmetries. So recall this is symmetries of an n-gon. So Dn is a subgroup of Sn, right? I mean, because you could think of it as moving your vertices around of order 2n. So in general, you have like n rotations and n reflections, right? As we saw for the square. The square had 4 reflections and 4 rotations, right? So the square is like d4. So dn is the set. I won't call set, but like it's generated by R and S, such that R to the n is 1, S squared is 1. So think of this as rotation, this as reflection, and it follows this law. So I don't write it this way, uh, but I tend to think so. But I'll go over that later. So is everyone clear on this, right? So it's clear that when n is 4, right? If you rotate 90 degrees, right? How many times until you get that this is 1 is the identity? Yeah, how many times until you get the identity? Well, you rotate 4 times, right? And for reflection, if you reflect and then you reflect again, you should get the same thing back, right? So some other books uh, they move the S to the other side. So if SRS is R inverse, you can multiply by uh, S inverse, right, on both sides. And so you get RS equals S inverse R inverse. Now, what is S inverse, everyone? What is the inverse of a reflection? Yeah, it's S, right? You get it from here, right? Because if S squared is E, if you like, some people use E. If I multiply, this is just S times S, right? So if I multiply by S inverse, I get S is S inverse, right? So the inverse is itself. So you get RS is SR inverse. So in other words, you could view this as, I can move any R past an S provided I invert, right? I invert it. So you see that this group is actually finite, right? From this law, because if I had, for example, I'm just gonna make it up. I don't know, like squared s r cubed, something like this, right? I could use this law and move all the r's to the, since these are equal, I can move all the r's to the left, right? So for example, I mean, here s squared is identity, so this is just s r squared s r cubed, which is, I mean, r and r squared is r cubed, right? Now what this law says is I can move this past the s, right? Provided I negate, right? I take the inverse. Now I get r s. This is just identity, right? So I get r s s, but s squared is identity, so I get r. Yeah. So so in general, you see that every element of Dn is of the form r to the n s, or r to the n. Okay, I take it back. Let's not use n, since I used n for r to the j. Yeah, where j is 0 to I guess I can use, yeah, where j is 0 to what? To n minus 1, right? So why does j run from 0 to n minus 1? It's because r to the n is 1, right? So r to the n is just r to the 0. So because it's order n. Is everyone clear so far? So you see, when I first write this, right, I can have like, I can have like 15 rs, I could have elements like these, but because of this law and this law and this law, I can write everything of this form, right? I could move all the r's to one side and then reduce it mod n because it's order n. And then s, it's either you either have an s or you don't have an s. You can't have two s's because s squared is 1. And it's similar, if you have 3s, that's the same as just having an s, because s cubed is just s squared times s, and s squared is identity. So is everyone clear with that? Yeah. So I guess so you see, if you have part A, you have part B for 37, right? Yeah, from what I just did, that's exactly what I just wrote. You can move the r's past the s provided you negate it. So I think for part A, I mean, to show this, I guess you just do picture proof. Yeah, draw a picture of an n-gon, and then okay, and then and then part C, it's the cyclic part, right? You have that theorem. It's exactly that theorem, right? Because r to the n is 1. So let me, right. So r is order n. So the group generated by r is cyclic. This is for 37, right? And then it's just that theorem. I forgot where it was. Let me see. Cyclic subgroups, I'm guessing. The order, yeah, right, right here. Theorem 4.13, right? It's exactly that. If you're a subgroup of order n, which is what we have, this subgroup R is order n. right? R to the n is 1 and nothing lower. Then, and R is the generator. Then if B is is R to the K, so theorem 4.13, if B equals R to the K, then order of, I'll write absolute value as order, yeah. Then order of B is N over D, where D is GCD of K. Yeah, and then you're done. That is exactly the statement 37C, right? Everyone good so far? Okay. So again, question. This should be easy from what I just wrote. Is Dn cyclic? Yes or no? No, cause yeah. What does cyclic mean? Cyclic means it's generated by one element, right? Here it's generated by two elements. It cannot be cyclic. So the next question is Dn abelian? So what does abelian mean? It means, in particular, it means this, right? Is this true? Is this what the law says? SR is RS. No, right? The law says SR is R inverse S, right? So it's not in particular abelian. It might be abelian if R inverse is R, but that's like if you think of how I say, if you think of rotation, the R squared, it's abelian for R squared and S, right? So R squared commutes with S because the inverse of R squared is R squared, right? If you rotate 180 degrees, then the inverse is you rotate 180 degrees. But if R is, R to the first power, the inverse is not R, right? Rotating 90 degrees, the inverse is rotating 270 degrees, right? So no. Okay. So everyone clear? Okay. Is everyone good so far? Hopefully I'm not confusing anyone. Okay. So let's move on. So did the professor go over, I'm pretty sure, so he went over dihedral groups on Wednesday and then I'm guessing he continued to cosets, right? Cosets today, or yes or no? What did he go over today? I'm guessing it's cosets, but okay, yeah. So let's talk about cosets. So if G is a group, so the reason we do cosets is because there's a big theorem at the end. So we define left / right cosets. So left coset. So the reason we do this is because G might not be abelian. So if G is abelian, left and right cosets are just the same, right? Because you could move, HG is GH, but left cosets of H with representative G is just this. set of GH, G lowercase h, such that H is an H. Now, this, right, so question, so I mean, an example would be EH is just H, right? Because EH is the set of E times H, such that H is an H, but E times H is just H, right? So the trivial left coset is just H. So H itself is a coset, right? It's EH. But in general, it might not be. And then similarly, right cosets is HG, right? So this is the set of HG such that H is an H. So you see, if the group is abelian, right, HG is GH, right? So left and right cosets coincide. Now, the point is different left, but let's just do left, different left cosets. It's same for right, so I'll put left slash right. Partition G. So what we're going to do is say G1 is equivalent to G2 if and only if. So remember, an equivalence relation partitions your set, right? So all you have to do is show it's an equivalence relation. I'll just do left, yeah? I mean, you could do the same proof for right. It's exactly the same. So there's a theorem in your book that says, what does it mean for two cosets to be equal? They're equal if and only if I'm, so this is the same as saying, if you think about it, it's the same as saying, if I multiply by G2 inverse on both sides, I get this, right? And being equal to H, you could check that this means this element is in H. Yeah, so it's a theorem in the book. Now, why is this an equivalence relation? Well, it's clearly so let's do transitive, right? G1 equivalent to G2, G2 equivalent to G3. Then you want to show G1 is equivalent to G3. Well, this, I mean, it means this, right? But the theorem shows that it means G2 inverse G1 is an H. This means G3 inverse G2 is an H. Now, what does this mean? Does it mean this? Well, let's multiply, not multiply, group operation it, right? So here I get G3 inverse G2, and then G2 inverse G1. This is equal to G3 inverse G1, which is this an H? Well, yes, it is, right? Because this element is an H by this assumption. This element is in H by this assumption. And H is a subgroup, right? H subgroup. So H is closed under your operation, right? So this is an H. And this exactly means that G1H equals G3H. And then you can check symmetric and transitive, yeah. No, symmetric and reflexive, sorry. Okay. Is everyone good so far? So you see here, so question is every left coset's same size as H, right? And the answer is yes, yeah. So I actually proved this. If you go to the, the lecture, the discussion video from last week, I guess, I did problem 27, yeah? And problem 27 is exactly, why is GH the same size as H? Well, that's the same thing as showing, group operation by G is a bijection, right? And 27, I think I proved 27, right? It's actually a bijection. So 27 problem 27 basically shows that, you know, all cosets are like the same size, right? So because you might wonder, right, like, can I multiply G, you know, can I get, like, if I multiply G to every element in H, can I get, you know, can two of them become the same thing, right? And the point is it can't. Yes. Okay, so question for the class is every left coset a subgroup? So H is a subgroup. What about GH, right? Sorry about that. So what about GH? So in other words, what about GH? Right, for G and G. So is this a subgroup? Yes or no? What do you all think? Yeah, no. I mean, I'll do an example. Let's take G to be S3 and H to be the subgroup. Let's do E and 1, 2. Yeah. So I have H, and then I just need to take an element not in H, right? So 1, 2, 3. What is this? Well, 1, 2, 3, you know, compose identity is 1, 2, 3. And then I need to calculate 1, 2, 3, 1, 2. What is that? So 1 goes to 2, 2 goes to 3, and then 3 goes to 1, and then 2 gets fixed, right? So this is equal to, so I have these two elements, right? And then you pick another element not in, you know, these two. So I guess 1, 3, 2, H. So 1, 3, 2 compose identity is 1, 3, 2. And then 1, 3, 2, 1, 2. What do you get? So 1 goes to 2, 2 goes to 1. So 1 gets fixed. And then 2 goes to 1, 1 goes to, so I guess it's 2, 3. Yeah. I mean, in this case, that's the only thing left, right? So you see, these cosets partition S3, right? These are all the elements of S3. But these are not subgroups, right? So be careful, right? I mean, it cannot be a subgroup because quite frankly, they don't have the identity element, right? Think about it. They must be disjoint from H. So an H has the identity. So it's not possible for the other cosets to be a subgroup. Okay. Is everyone clear so far? Okay. Now here's a question for the class. You can think about this. If I define, so I'm gonna so there's something to think about, right? I'm not gonna go over it because that's for later, but let S be the set of left cosets. Yeah, so for example, S is H, 1, 2, 3, H, and 1, 3, 2, H. Yeah, yeah. I don't know why I erased that. in example above, right? So, in general, like, I mean, it depends on what the group is, but in general, it's H, G1H. Let's assume G is finite for now, yeah? Just so I could write like Gn. Okay. If I define G1H star I'll use GI and GJ, yeah. GJH to be GIGJH. Does S form a group? Identity is clear, right? Because H, this is the identity, right? This is EH, right? Remember, I told you right here, from right here. EH is just H, right? So identity certainly holds, but does S form a group? So that's a question for you all to think about. The answer is no, but try to figure out why. I'll say no, not always. Yeah, the answer is not always. But okay, so since left cosets partition G, I don't know why I wrote that. Left cosets of H partition G, right? I can we define GH to be number of left cosets, right? So you see in the example above, S3 to H is 3, right? Because we had 3 left cosets. We have 1, 2, 3. Yeah. And you could see that it's just this, right? That's the order of S3 divided by order of H, because they're all the same order. So here, the order of S3 is 6 and H is order 2. So it's 6 divided by 2. Okay. So from this, and this is Lagrange theorem. So G finite group, and let H be a subgroup of G. Then absolute value of this means order, right? Is the index is number of distinct left cosets. Yeah, I need to write distinct. Distinct left cosets of H and G. So what does this mean? It means in particular, order of H divides order of G, right? So this is Lagrange theorem. Lagrange theorem means if G, basically it's saying if G is a finite group, H subgroup, the order of H must divide, the size of H must divide size of G. Yeah, so in the example, right, like Z6, like Z mod 6C, if you like, or this is like this. If this is G, any subgroup, you cannot have subgroup of order 5. Yeah, there cannot be a subgroup of size 5 by Lagrange, right? Because 5 does not divide 6. So you see, you could only have subgroups of size 1, 2, 3, and 6, which is the whole group, right? So That's, I mean, and it's pretty strong, right? So question, what if is P prime? What subgroups are there? If the order of G is prime by Lagrange, what possible orders can I have? So okay, if order of G is prime and I have a subgroup by Lagrange, the order of the subgroup must divide P. So what numbers divide a prime? What possible numbers can you have that divide P if P is prime? Like, for example, 7, 13, or like take P to be 7. What numbers divide 7? No, divide, not multiple. like numbers that divide 6 are 1, 2, 3, and 6. Right? Like I think you're thinking of multiple, not division. Yeah, 1 and 7, right? I mean, the only divisors are 1 and P. So you see, so for any subgroup of G, either it is trivial, either it is, if it's order 1, and by definition of group, you must have identity. It has to be just the trivial subgroup, right? It is E, or it's order P, which is just the whole group, or whole group, right? And you've learned this before, right? For Z mod P, like PZ, right? Or if you like every non-identity element generates the whole group, right? You all learned this, right? Because any number is co-prime to P, right? And you learn that co-prime numbers generate Z mod NZ, right? So this is an example of that, right? Like you either get just the identity group or the whole group. Everyone clear so far? Right, and it's stronger in a sense. I mean, if order of G is 24, yeah. So like example would be like S4. S4. So S4 cannot have subgroups of order. So no, it's divide, right? So it's not enough to just share a factor. You must divide. So like for example, 14, you cannot have because 14 does not divide 24, right? Like 7, I don't know, 13. The list goes on and on, right? So if you don't divide 24, you cannot be a subgroup. So you see Lagrange is pretty strong, right? Now a corollary of this is if G is finite, G is in G, then the order of the element divides order of G. So this is immediate, right? Because what's the order of an element? This is just, I mean, if this is like K, then the subgroup generated by G has order, this is like the order of the set, right? This has order k, right? So recall the subgroup generated by the element is you take all powers of it, right? So this is order k. So by Lagrange, this the subgroup generated by G, like must divide order G, but this thing is equal to this. So this means size of group. So when I put absolute value, this means that, but here it means order. Yeah. Is everyone clear on why like the group generated by G is just the order of G? Because like if G to the K is E and nothing, and G to the J. So this is what it means to have to be order, right? G to the J is not E for J equals 0, not 1 to K minus 1, right? That's what it means to be for the order, right? It means there's no, it's the smallest positive number. But then what is subgroup generated by G? It's all powers of G, right? So it's G0, G1, G2, G3, GK, right? And then so on and so forth, right? But if you are order, if this is G to the K is E, G to the K plus 1 is just G, yeah? It's just this. So you see, you are repeating past K, and you see that from here, well, if G to the K is E, then G times G to the K minus 1 is E, yeah? By exponent law, I mean, like, right, because, but then this means G to the K minus 1 is G inverse, right? That's what it means to be the inverse, right? It's the inverse of G. I feel like this is just G. G to the first power is just G. And then similarly, G squared times G to the K minus 2 is E. So G to the K minus 2 is G negative 2, right? So you see, I didn't write it, but G to the K minus 1, comma. So like this is just this. And then G to the K minus 2 is just the next one. So everything here is out. So and then similarly, G to the K is just identity, right? So you see that the order is just this. The order of an element coincides with like the order of the group generated by that element. And then from here, you see that it must divide order of G by so this is by Lagrange. Everyone clear so far? Hopefully not too confusing. Okay, so let's move on. So there is a tower law. So the nice thing is cosets work very nicely. So let HK be subgroups of finite group G. And you have G is contained in H is contained in K. Then, the index of G to K is just you go G to H and H to K, right? It's, I mean, to convince yourself, this has this order, right? And this has this order. So at least, if you're not convinced, the orders match, right? Because the size of H cancels. So that's one thing. Okay. So note converse to Lagrange is false. Yeah, so remember, if I told you if I have a group G of order n, any subgroup must have order dividing n, right? So so I guess I wouldn't really say converse, but so, instead I'll put note Lagrange does not imply existence of subgroups. So you might ask, right? So the question you might ask is, if order of G is n and D divides n, if I just pick any divisor, does there exist a subgroup of order D? Right, so I'm kind of going backwards, right? Because before I said, if I do have a subgroup of order D, D must divide n, right? So it's kind of like the converse, right? So now I'm asking, if D divides n, does there exist a subgroup of order D? And the answer is no. So it's in your book. So the example in book is A4. So this is the even cycles, right? Cycles that could be written as even transpositions as a subgroup of S4. And so this is order 12, right? Because it's half the size of S4. So it's 24 divided by 2. And they basically show no subgroup of order 6. Right? Because 6 divides 12, but you know, Lagrange does not say whether there is a subgroup of order dividing whatever the group is. It just says if you do have a subgroup, then the order of that subgroup must divide the order of the group. Everyone clear? So I mean, I could pinpoint you probably. Yeah, right here. Yeah, it is the converse. So A4 has no subgroup of order 6. And I think the proof of this is yeah, so I think if you read the proof of theorem 6.16, the second part, it basically tells you the, what do you call it? I think the answer to your second, to that other question. It's a pretty nice result that if you conjugate, it's just applying the cycle. So let me just, for those of you who don't know what I'm talking about, sigma tau inverse is just tau applied to sigma. What do I mean? So like an example, let me just do an example. You could show it there. So this thing is, I don't know what, like 1, 2, 1, 2, 3 inverse. You can do the whole thing. But this is just if this is tau, to this tau inverse. This is tau. This is sigma. This is tau of 1, tau of 2. Yeah. So if we just follow this description, where does tau take 1? Well, tau is 1, 2, 3. So tau takes 1 to 2. And then where does tau take 2? Tau takes 2 to 3. Yeah, so I mean, it's just a faster way of computing, but yeah, okay. But I think it uses that fact to prove A4 has no subgroup of order 6. Yeah. Everyone good? Okay, that's all I have for today. I think he should be going over Fermat and Euler next time. So that will be what we do next time. Everyone good so far? Or good? Yeah, okay. All right, bye.